uh, session. Today we're going to work on RC circuits. So this is the other worksheet which I have. RC circuits, R standing for resistor and C standing for capacitor. So you can see this is straight from, actually from the last outline. You have a battery, a resistor, and a capacitor. So you got these equations, which I'll explain what they are, but we will not really need them very much. AP, I can't imagine they'd put it on there, but you're expected to kind of understand why is it an exponential. So this is an exponential decay equation. Probably doesn't make too much sense right now, but the main idea of this capacitor resistor thing is that you have your battery here, right? So it starts. Let's see if I can get some little. If I get you get your plot positive here, so the current flows, right, and charges this capacitor. Is the idea. So the capacitor has some charge on this, but the resistor obviously takes away some voltage, right? And we're not really going to, AP doesn't really use this type of circuit. This is just an R and C, that's it. So over the resistor will basically determine how fast the capacitor charges, and that's really what this is right here, this the time constant, right? So for those who remember PERT, right, from your math days, you get P equals P, whoa, P equals P 0 e to the RT, right? Remember that? Remember PERT, which is like you have your principal amount. That is pathetic. Your principal amount there. Why is it so? There we go. Okay. So you get your P right there, which is like how much you start with, right? That's like your principal amount. And then you gain with interest. The R was like how fast your interest increased. This is like your amount you'd have at any point. So this is actually, these equations come from the fact that once you charge the capacitor, so charging is a little bit different. This is basically, these are equations supplied by the capacitor. So once it's charged, and we talked about this in the other video, once it's charged to whatever voltage, right, then you actually disconnect this, and then you can close this off and let the capacitor discharge. And that's what this is basically saying, right? These equations are talking about the discharging part, where the capacitor starts with some sort of voltage, and then over time it gets less and less and less. It starts with some charge, and over time it gets less and less and less. And it starts with some current initially, and over time it has less and less and less. So all of these look something like this, where you have like an exponential. Here's either your initial voltage. So let's pretend this is 1.5 volts. This would have been charged to 1.5 volts. If the battery is still connected, it's not going to charge any more than 1.5 volts. This is a discharging equation, so not really shown in this picture. But the voltage over time will decrease. And guess what will also decrease? The charge on the capacitor will decrease, and the current will decrease. So a lot of questions will ask, like, what's the current initially, or what's the current final? We're not, we can use these. These are actually, I put some sample questions, number 11 and 12, if you want to try them out. I would say not as important. This is in the previous problem set, right? So I didn't really go over that because it's not super important. That was in the chapter 30B packet, right? So capacitors charging and discharging. So what really AP likes to think about or focus on is this idea, right? So this is your chapter 32C outline. And you got your battery here, and you have your little switch. So right now, nothing's happening. You have a resistor, and you can kind of see that these guys are in parallel, right? So you have your resistor and your capacitor in parallel, and you have a resistor ahead of time. So it's a little bit different. This one right here was not there, like in the previous example. But this is a little bit more typical. You'll see why in a second. So you close this switch, right? So you close this switch. So guess what happens? The current starts flowing this way, goes through, and at this point it comes to a junction, right? So switch close. I'm going to draw a picture of this was notes from class. You close the switch, all the current flows to the capacitor since there's no resistance. What does that mean? Well, when it comes to like the current comes along here to this point, or I'm just going to redraw the picture, it's going to have a choice. Does it go down to this resistor? That seems like a dumb idea because it's got resistance. Or it can keep going along here. Basically at the beginning, the capacitor acts like a wire, right? So here's your capacitor, right? You got your capacitor here, and basically there's no charges on it. So guess what? All the current will flow this way, and that's basically what's going to happen. Right, the initial current flows to the capacitor. Oh, sorry, I forgot this guy. Going to go through this 3 ohm right here. That 3 ohm right there is going to go through that guy. This guy is pretty much irrelevant, right? Because why would current choose to go through resistance when it has nothing over here? Now guess what? As the capacitor starts charging, things change. More current begins to flow to the resistor, right? So that's just at the beginning, this guy right here. So I'm going to not put that there because that's only initially. So if they say, what's the initial values, you'd think this is your circuit right here, okay? If you then as time goes on, what's going to happen? You're going to have this resistor is always here, and then it is going to have a choice. Some of the current's going to go down, some of the current's going to go that way. So yeah, you'll have this, you'll have that. It's going to keep flowing to this, but slower and slower, right? So here we have our, basically, this is going to be our I1 right here, and your I2, and so current splits. So whatever the current was coming out, now it's splitting into these two pieces. So it's still flowing out of here, and it splits. So slowly, this is the beginning, so this is your initial amount. So now it starts splitting between the two. How much will this capacitor charge to? And a lot of people want to say, oh, 6 volts, right? Because hey, there's 6 volts here. But think about once it's charged, once this capacitor is charged, this is our next little picture here. Once it's charged, so here we have capacitor has been charged. Capacitor has been charged. All current flows to the resistor. Since the capacitor's at, that should say 3 volts, sorry about that, should say, since the capacitor's at 3 volts. So once this, like think about what this circuit would be in the final circuit should look something like this, right? So once the capacitor is fully charged, you get 3 ohms, you get 3 ohms. So what if I just told you this circuit, right? Pretend there's not even a capacitor attached. The idea here is going to be if you have a 3 ohm and a 3 ohm, go ahead, figure out what's the overall resistance, 6 ohms, right? Your overall resistance is 6 ohms. Let's see if I can actually do this, 6 ohms. V equals IR, you go ahead and do V equals IR, and you should get a current of 1 amp, right? So 6 volts, 6 ohms, you get 1 amp of current. So 1 amp's going through here. So each of these guys, if you do 1 amp times 3 ohms, you get a 3 volt drop here, you get a 3 volt drop here, and which means if this is in parallel, if this guy right here, this guy is getting 3 volts, then this guy must get 3 volts. So that was incorrectly, the capacitor gets 3 volts. In the previous example, let's pretend it was just let's go back to this. If this was 6 volts, this also would be 6 volts. That's why I did miswrite that. Maybe I corrected it on your version, but so if it's just a resistor and a capacitor, it gets the full voltage, right? Because it's just a series circuit, so it gets all the voltage at the end. Here, it's only going to get 3 volts. Whoops, sorry. It's going to get 3 volts. And hopefully you can see that current still flows, right? This capacitor is charged, which is kind of cool. This is like how the old cameras, you used to have to like wait for your camera. Maybe when you were little, you had to like charge up the bulb, right? You like on those, maybe those throwaway cameras, right? You're charging up the bulb. Once it's ready, then this can keep flowing here, right? This keeps flowing, it keeps flowing. This is just a regular circuit, and you just charge this capacitor over here, so it's just hanging out there. So now what happens if you open the switch, right? So if you open the switch, wait a second. Now, that means no current is flowing out of the battery anymore once you open the switch. Once you open the switch, basically what you have is you're going to have this right here. Let's go. This is your circuit right here, right? Because this whole part is gone, right? This battery is not flowing anymore. That resistor is kind of just sitting there. So what you end up with at the end is going to be a circuit where you have your 3 ohm, you have your capacitor, like this. So you have your 3 ohm, you have your 3-volt capacitor, and it has positive charges here and negative charges there. Guess what's going to happen? Current's going to start flowing that way. So once the capacitor is charged, you should figure out that like the current is going to go around this way. So it's sort of like you charge it this way, charge it clockwise, and then it discharges counterclockwise, and you have to have this sort of circuit, right? If you try to discharge this capacitor, like if you disconnect the battery here, you've got to somehow make this a circuit, right? So what's nice about this other version is that you just open and close the switch and you get a charging and then a discharging through this resistor, right? So through this 3 ohm resistor here. And that's the discharging follows all those equations, right? So like when it discharges, it's at 3 volts. Whoop, it's going to be at 3 volts. Its voltage over time is going to be 3 volts. And then so it will discharge, but not a constant 3 volts, not a direct current of 3 volts. So you can have, what's cool about capacitors inside a circuit, you can basically have mini little batteries that give surges of electricity, and that's obviously part of electrical engineering. So with that in mind, there's this right here. If you look at your, so here's the, right, so this is what we just did. It's posted. You have a nice answer sheet of this. But the example on the back, so things like calculate the initial current, right? Calculate the initial current on this. Whoops. So if I said calculate the initial current, hold on one second. Let's go with, there we go. I'm just going to step you through this without a pen since I don't have it on PowerPoint. Calculate the initial current through R1. Well, guess what? At the beginning, right, you don't count this middle part. Don't count R2 here. The current's just going to flow around the outside here, flow around the outside. So that's how I get this. Look, I draw the circuit. I don't draw R2 in there because initially all the current will flow here. And when I say initially, first microsecond or two. So that's just the initial current. It will obviously change. Calculate the final current. The final current, when this is fully charged, boop, get rid of this guy. You just have your normal circuit. You just have a 5 ohm and a 5 ohm, right? So that one's gone when it's fully charged. Calculate the voltage before and after. Well, before, what's the voltage in R1? Before, it's going to be all the voltage goes through him. So here's the before picture. This acts as a wire, right? So he gets all the voltage initially, all 20 volts, but then over time, what happens by the end is you have 10 and 10. You have this is your new scenario. So you get 10 volts here, 10 volts here. The initial circuit was without this guy, so 20 volts to R1, and then afterwards they split the volts. And that's what they're asking here, the same thing. At the beginning, there's no voltage in R2, right? R2 is this guy right here. And then afterwards, he gets 10 volts. So it's sort of like 20 for this guy, and then 10 and 10, right? 20 and 0, and then 10 and 10 by the end. And then you can figure out how much charge is stored in the capacitor. Does he get all 20 volts? Does the capacitor get all 20 volts by the end? No, remember what we said. He's attached to this guy here. He's attached to R2. If he's attached to R2, he only gets whatever voltage R2 has. So he should get 10 volts. He should get 250 microcoulombs of charge because we know his capacitance. Doesn't matter what happens during this, the capacitance doesn't change. So it's in parallel, so he gets the voltage to whatever he's attached to. So hopefully that helps a little bit, just give you a little background of the RC circuits. And there actually is another really cool, this is more detail. I don't want to go into it too much, but this really explains. There's like a note sheet I got that I found that talks about the initial current and the final current, and it actually goes into what the time constant is. But I'd rather focus on just do you understand how an RC circuit works, because there's a differential equation for the charging. So I will go into this later, but it's not critical. It talks about where all those E formulas come from. So if you want to look at this, go ahead and you can ask me questions on it. I'm not going to focus on it. And then there's some AP problems that have this in them. So if you look at the later circuits problems, which I'll talk about this week. All right, well, hopefully that was helpful, and talk to you later.